Travis. Hi, Wayne. This is John Whitaker for the Probability 1 graduate level class, and this is our 16th video lecture. Today we're going to talk about continuation of some more types of convergences. In particular, we're going to talk about almost sure convergence, and we're going to talk about convergence and probability, which we saw a large number was. And then we're going to talk about the strong law of large numbers and prove it with an additional condition to what the theorem actually says. But let's go ahead and get started by looking at some different types of convergences. So I want to talk about almost sure convergence. So here's the definition. So let F sub n be a sequence of functions defined on a common domain. So all of them have the same domain. A, which is a set of all. Okay. Then F sub n converge almost surely. So AS with respect to a probability P to a function big F on A if what? That's right. The probability of the set of all x's elements of A such that the the limit, well, I should say it this way, such that the limit as n goes to infinity of the absolute value of f sub n minus f of x, or minus big F, is greater than or equal to epsilon. If that set equals to 0 for all epsilon greater than 0. That's our definition for almost sure convergence with respect to a probability measure. What that means is that is the set where f sub n of x does not converge to big F of x has probability 0. Okay. Or is 0. So I shouldn't. The probability of the set. Let me write it that way. That is the probability of the set. Yeah. Where f sub n of x does not converge to let's look at an example. So if we look at that same example we have, we're going to find f sub n of x to be equal to x to the n on, and so our a here is again 0 to 1, close. Then f sub n of x converges almost surely with respect, I'll just say almost surely, I'll talk about probably in a second, to, I'll call it f star equal to 0 on A, where the probability it's not exactly right, is the smallest length of the interval, okay, that contains the set. That's the way we're going to define the probability of a set. It's the smallest length of the interval that contains the set. So it's the length of the smallest interval, if you will, the smallest length that contains the set. And so here, the x sub n's, the f of x sub n will converge to 0, except at x equal to 1, so what we're thinking is that we notice, okay? So note the set where f sub n of x does not converge to 0 is 1, and the probability of the set of 1, we talk about what's the smallest interval that contains 1, will just be, even though it's not an interval, it would be tending towards 0 in terms of its length. Okay? So that's why we define the probability to be that. As a fact, pointwise convergence. So if f sub n of x converges pointwise to a function f on A, then f sub n of x converges almost surely with respect to a probability to that same f. So pointwise convergence implies almost sure convergence. But we can see from the previous example that the reverse doesn't hold true. In the previous example, we had almost sure convergence to the function that was 0. But remember, the pointwise convergence is to a function that isn't always 0. It's 0 almost everywhere. It's 0 except when x is equal to 1 for the pointwise convergence. The next thing we want to look at is this convergence in probability, which we said the weak law of large numbers was an example of So here is a definition. A sequence of functions F sub n of x defined on the common domain A, okay, which is a subset of R, converges to a function f on A in probability if, so here it's the limit as n goes to infinity of the probability of the set of all x's element of A, such that the absolute value of f sub n of x minus big F of x is greater than or equal to epsilon. If that goes to equals to 0, and that's true for every epsilon greater than 0. And that's our definition. And we'll look at an example of that in a second. First, we have a fact. And that fact is, if f sub n of x is a sequence of functions converges to f of x on A in probability, then the f sub n of x converge I made a mistake, okay? I said it exactly backwards. So if f sub n of x converge to f of x on A, almost surely, that's what I should say, almost surely, with respect to a probability, then f sub n of x converge and probability to f. But the reverse order doesn't hold true. I almost made a mistake when I was writing. So as an example to see that, okay, example to show convergence in probability does not imply convergence almost surely. All right, let's consider this sequence of functions. Okay, we're going to find f sub 1, and I'm going to do it pictorially. I'm going to find all the functions pictorially. There, f sub 1 is going to be defined on 0 to 1, and it's going to be defined to be 0. So f sub 2 is going to be defined to be equal to 1 on 0 to 1. It's always 1. Now, f sub 3, I'm going to define pictorially as well. What I'm going to do is for f sub 3, I'm going to split up 0 to 1 into 0 to a half and a half to 1. And then I'm going to define f sub 3 to be equal to 1 on the first half of this interval, and then 0 on the second half. And then f sub 4 is going to be very similarly defined. I'm going to break up 0 to 1 into 0 to a half and then a half to 1. And I'm going to define for f sub 4 for it to be 0 up to 1 half, and then after 1 half, it's going to be defined to be equal to 1 from 1 half to 1. All right, let's do a few more pictorial representations for how I'm defining this sequence of functions. So here we had, before we move on, we had two functions kind of coupled together, and then we have these next two functions coupled together. And then what I'm going to do is have 4 functions coupled together. Then we'd have 8 functions coupled together. But the next 4 functions continue on powers of 2. But the next ones I'm going to group, so f sub 5, it's going to be, I'm going to break up 0 to 1 into 0 to a 4, 4 to a half, and 3/4. Well, that's what I'm going to do. But and here we're going to have 1 on the first quarter, and then 0 everywhere else. Okay? And then f sub 6, again, go from 1/4, 1 half, 3/4 to 1. And I'm going to have start off at 0. And then the only part where f sub 6 is going to be 0 is just over the region from 1/4 to 1 half. And then if I look at f sub 7, I'm going to move the part of where it is non-zero to be from 1 half to 3/4. And the rest of the time it's going to be 0. And then f sub 8, the part where it is non-zero, will just be from 3/4 to 1. And so we continue on in this pattern. So the next one will have 8. And what I mean in this pattern is that the region where the function will be non-zero, will be 1, will be over a region that's only 1/8 of the unit long. And so when we look at this, continue with this pattern. To form the sequence f sub n of x. A sequence of functions. And what you can see is that, in this grouping of 4 functions, the set where it's non-zero has length, if you will, 1/4. And my next 8 grouping of functions, the spot where the function will not be 0 will have measure, if you will, probability 1/8. And then for my next 16 groups of functions, they will be non-zero over different regions, but each one of the regions will have length probability of 1/16. And so the spots where the functions are non-zero, they're getting, in terms of their probability, smaller and smaller and smaller. So f sub n of x converges in probability to f of x equal to 0, but does not converge almost surely with respect to a probability, with respect, I'll say, to the length probability. And so measures intervals by their lengths is this probability that I have in mind. Okay. And it doesn't converge to zero almost surely, because really it doesn't converge for any point. Here, just take a point in here. Lots of times it's zero, but every once in a while it's going to jump up because of the way the functions are defined and changing to be 1, that it's going to jump up to be non-zero lots of times. Okay, so that's my example. So we had those 3 types of convergence. And in the weak law of large number, we had convergence in probability. Well, there's something called the strong law of large number. And it has to do with convergence almost surely. So here's what it says. Here's the theorem. Strong law of large numbers. That's what it's called. It says, let x of 1, x of 2, x of 3, going on forever, be a sequence of independent and identically distributed random variables. Each with finite meaning the expected value of x of I equaling mu. Okay. Then, with probability 1, that means almost surely with respect to this probability, x of 1 plus x of 2 plus x of n, okay, over n, that converges to mu. So almost surely does this function converge to this constant. Okay, we want to prove that. I should say something here. So it not only has expected value x of I and should have variance, so finite variance of x of I equals to sigma squared. And so insert that. Okay, so we want to prove this, and so I'm going to assume the hypothesis. We're going to let x of 1, x of 2, x of 3, and so forth be a sequence of independent and identically distributed random variable each with finite meaning u equal to sigma squared. Okay. We'll also, even though the statement is true as stated, we'll also prove it with additional hypotheses. We will also assume this makes the proof more manageable, okay? That the expected value of x sub I raised to the fourth power is finite. These expected values may not be finite, but we're going to assume that they are. Okay. What we'll do is we'll consider, well, we'll break it into cases. The first case, case 1, is we'll assume mu equals to 0. Okay? In both cases, we will consider, so I'll write this down. Consider S of n equal to the sum as I runs from 1 to n of S sub I. X sub I. So just the sum of the X sub i's. Okay. All right, so suppose mu equals to 0. Okay. Now, examine the expected value of S of n raised to the 4. So, what is that? Well, that's equal to the expected value of x of 1 plus x of 2 plus all the way to x of n times x of 1 plus x of 2 all the way up to x of n being added here times x of 1 plus x of 2 plus all the way up to x of n times x of 1 plus x of 2 all the way up to the addition of x of n. All those guys will be multiplied together to take the expected value back. If you multiply all of that out and try to take the expected value, you can break up the sum, the expected value of the sum, into the sum of expected values. And what you see is that you will get terms of the following form. So we will obtain, so the expected value of S of n to the 4 will consist of the addition of terms of the form. Okay, so there's several forms. One of them is x of I to, so it consists of addition. Expected value of x of I to the 4. Then you can have the expected value of x of I to the third, x sub j. Then you can have the expected value of x of I squared, x sub j squared. Then you can have the expected value of x of I squared, x sub j, x sub k. And then finally, you have the expected value of x sub I times x sub j times x sub k times x sub l. Okay, so there's those types. So there's 5 of them, types of expected values. Here's what I want you to know. Okay, I can't say anything about the expected value of x sub I to the 4 very quickly. But this guy, x sub I cubed times x sub j, because of independence, will be equal to the x of I to the third times the expected value of x of j. But we're assuming in this case that the expected value is mu is equal to 0. So this is just 0. Also, the expected value, well, I can't say anything about this guy, but the fourth one over here, the expected value of x squared times xj times xk, that's equal to, because of independence, the expected value of x sub I to be squared times the expected value of x sub j times the expected value of x sub k. And that, these two guys here are mu, which is in this case 0, so we just get 0. And this last guy, let me write it out, will also be 0. So I'm going to write that down. So the expected value of x sub I, x sub j, x sub k, x sub L, that's going to be equal to, due to independence, expected value of x sub I times the expected value of x sub j times the expected value of x sub k times the expected value of x sub L. Each one of these is mu, and that's equal to 0. So what we were looking at was the expected value of s of n to the 4th. And what I know is it's going to have the expected value of x sub I raised to the 4th, where how many x sub i's raised to the 4th will be involved? Well, there would be n of them. Well, let's write it down this way. It would be the sum as I runs from 1 to n. And they're all the same. Okay? And then it would be plus, and we have some sum of the expected value of x sub I squared times x sub j squared. That's the only other types of terms that we have. How many of we're going to have, I don't know just yet. Okay, this is nothing more than n times the expected value of x sub 1 and, to the 4th. And the reason that that's true is that each one of these random variables are identically distributed. And so the expected value of some function of any one of them is the same for all of them. So that's what we have because they're identically distributed property. Plus, now there's a question about independence here. Not a question, but the fact that you have independence gives us some sum of the expected value of x sub I squared times the expected value of x sub j to be squared. Okay. So I'll write this down as the same again. Plus, I'm not saying how many there are here, but even though these aren't the same random variables, again, because of the identically distributed property, these quantities are going to be exactly the same. So I'll write them down as the expected value of x sub 1 squared. To be squared. So this is like x sub 1, the expected value of x sub 1 squared. This is like the expected value of x sub 1 squared. And we're summing up a bunch of those. How many of them? Well, I don't know. Remember what the s of n to the 4th was? It's where we're multiplying x sub 1 plus x sub 2 all the way up to x sub n times itself 4 times. How many times am I going to have pairs of them, well, like x sub 1 squared and x sub 2 squared? Okay. So let's think. Well, first of all, here's the way that you can think about where they would come into play. You would have to do this. You would say, well, to get the random variables that are involved, like x sub 1 and x sub 2, that each one of them is going to be squared, you'd have to choose 2 of the random. The number of ones I'm going to have are n choose 2 of them. Okay, so we had x sub 1, x sub 2, all the way to x sub n. That's n random variables. We choose 2 of them to be involved as x sub I and x sub j. There's 2 differences. Okay? So once I choose one, there are 2 of them. So there n choose 2 ways to do that. One of those ways, one of those outcomes, is we have x sub 1 and x sub 2. And when I think, how can I get x sub 1 and x sub 2 involved in multiplication, or how many times are they? Well, you could have x sub 1 from the first n sum random variables together. You could have x sub 1 from the second, and x sub 2, and x sub 2. Or you could have had x sub 1, x sub 2, x sub to x sub 1, and you can vary these. And so the number of ways that you can have them is out of those four sums, x sub 1 through x sub n, you're going to pick two of them to come out to have x sub 1. And then out of the next two, the remaining, you pick two of them to be x sub 2. And so there's 4, choose 2. Okay. So this ends up yielding n times the expected value of x sub 1 raised to the 4 plus 4, choose 2 is 6. Here this is n times n minus 1 all over 2 factorial. So remember, this is n factorial over n minus 2 factorial. That means n times n minus 1. And then we have 2 factorial on the bottom, so I'll just write down 2. And then the expected value of x sub 1 to be squared. Well, this is equal to n times the expected value of x sub 1 raised to, assuming that's finite. Here we have plus 3 n times n minus 1 times the expected value of x sub 1 squared to b squared. Well, n minus 1 isn't as big as n, so I'm going to replace that with n. Just n times the expected value of x sub 1 raised to 4 plus 3n squared. The expected value of x sub 1 squared to b squared. Now, I'm assuming this is finite, and so here's what I can tell you. The expected value, since the variance of x sub 1 squared is greater than 0, then what we have, what was the variance of x sub 1 squared? What that's going to be is the expected value of x sub 1 squared to b squared, so it's x sub 1 to 4, minus the expected value of x sub 1 squared to b squared. That has to be greater than 0. That means that the expected value of x sub 1 raised to the 4th is greater than or equal to the expected value of x sub 1 squared to b squared. So I'm going to replace in here, in this expression, I'm going to replace the expected value of x sub 1 squared to b squared by something bigger. So what I get, remember, we're talking about the expected value of s of n raised to the 4th. What I get here is n times the expected value, well, I should say less than or equal to, n times the expected value of x sub 1 raised to the 4th plus 3 times n squared times the expected value of x sub 1 to the 4th. That's what I'm replacing. These are the same things here. And so what I'm going to do is I'm going to divide everything by n to the 4th. So the expected value, and I can bring that into the 4th inside, of s sub n raised to the 4th over n to the 4th will be less than or equal to the expected value of x sub 1 to the 4th over n to the 3rd plus, here this would be 3 times the expected value of x sub 1 to the 4th over n squared. Okay. Therefore, so if you sum as n runs from 1 to infinity of the expected value of s of n raised to the 4th over n to the 4th, that's going to be less than or equal to the sum of each one of these guys. So n runs from 1 to infinity. It was expected value of x of 1 to the 4th over what it should have been. Yeah, that's what I wrote. Plus, and I break this up to another sum. It's n runs from 1 to infinity of x sub, the expected value of x sub 1, this is the fourth, this was times 3 over n squared. Now these expected value of x sub 1 to the fourth, we're assuming that that's a constant. So this is a constant over n to the third, we're summing that up. That ends up being a power series. By calculus, we know that it converges. So what we get is that, well, the infinite sum of the expected value is the same thing as the expected value of the sum This is going to be finite. So it'll be less than infinity, because each one of these is finite. Okay? And that implies that the sum let me check something here for a second. So that implies that the sum of s sub n to the fourth over n to the fourth is finite. Okay. With probability one. Sure. Because if not, then there would exist a set whose probability is non-zero. Such that the sum as n goes 1 to s of n over raised to 4 over 4 is infinite. And thus, this expected value of this sum would be infinite. Okay, because you have some form of infinity times some number for that probability of that set. And that would be infinite. So since that sum of the s of n to the fourth over n to the fourth is finite, since sum n goes to 1 to infinity of s of n to the fourth over n to the fourth is finite, probability 1. Okay. Then what that means is that the limit as n goes to infinity, s of n to the fourth over n to the fourth must go to 0 by the divergence test with probability 1. Okay. What that means, that forces the limit as n goes to infinity of s of n over n to be equal to 0. with probability 1. And so we get the result in this case that we want, so the limit at n goes to infinity of x of 1 plus x of 2 plus x of n over n. That equals to 0 with probability 1. So we don't have a different case to consider. But it's easy. We just make use of the first case. So in case 2, what are we doing? We assume mu is different from 0. Then consider the sequence of functions x sub I subscript star equal to x sub I minus mu. So when you look at these functions, then the expected value of x sub I should say, then the x sub I stars, because the x sub i's were identically distributed and independent, these x sub I stars will be, I can set the sequence, will be a sequence of independent and identically distributed random variables. And the expected value of x sub I star, which equals to the expected value of x sub I, x sub I, minus mu, which is equal to the expected value of x sub I, minus the expected value of the constant, is just mu, which equals to 0. And so, x sub I stars, that sequence is just like case 1. So by case 1, with probability of 1, we have that the limit as n goes to infinity of x of I, x of 1 star plus x of 2 star plus all the way up to x of n star being added over n equal to 0. So with probability 1, the limit as n goes to infinity of x of 1 minus mu plus x of 2 minus mu plus all the way up to x of n minus mu over n equals to 0. That says, so with probability 1, the limit as n goes to infinity of x of 1 plus x of 2 plus x of n over n minus n mu over n, which is just mu, equals to 0. So that says with probability 1, the limit as n goes to infinity of x of 1 plus x of 2 plus x of n over n equals to mu. And in all cases, we got the desired result. So that concludes the proof of the theorem. Okay, we have one more limit theorem to go. We thank you very much for your time and patience.